In this lecture, we're going to describe each of the defining characteristics of molecular, ionic, non-bonding atomic, metallic, and network covalent crystalline solids. Recall that our crystalline solids have their molecules, atoms, or ions arranged in a well-ordered three-dimensional array, while amorphous solids do not demonstrate this characteristic long-range order. The first step in classifying the crystalline solids is to determine if they are made up of molecules, ions, or atoms. Next, we need to think about how these components are held together in the solid, both on the intramolecular and the intermolecular level. Let's take a moment to review those forces now. Recall that our intermolecular forces are the forces between units and include dispersion forces, dipole-dipole forces, hydrogen bonding, and ion dipole forces. The strength of these forces range along a rough continuum from weakest to strongest, as shown here. In order to round out the list, we really need to include the intramolecular forces, or the forces that hold ions and molecules together, shown in blue. We see that the electrostatic attraction between ions is fairly strong in ionic compounds, but not quite as strong as the covalent bond or the sharing of electrons we see in molecular compounds. Let's keep these forces in mind when classifying solids, because the stronger the forces involved, the higher the melting point of the solid will be. As the name implies, molecular solids are made of molecules which are held together in the solid by intermolecular forces. Since most intermolecular forces are relatively weak, they are easily disrupted by adding low amounts of heat. Think about ice, for example, which melts at 0 degrees Celsius. Ice is a molecular solid held together by dispersion forces and hydrogen bonding. Let's look at some more examples. Dry ice, or solid carbon dioxide, is a molecular solid, as is sulfur dioxide and benzene, C6H6. While these three examples are easily recognizable as molecules, we see, too, that there are some elemental examples we need to consider. For example, we know that there are 7 diatomic elements, including iodine, and there are elements that have several allotropes, or different physical forms in which the element can exist. Sulfur typically forms long chains and S8 rings, as shown here, while phosphorus can form separate tetrahedral molecules, which are known as white phosphorus, or it can form linked tetrahedra, known as red phosphorus. Our next category of crystalline solids are the ionic solids. Recall that ionic compounds result from the complete transfer of electrons from metals to the nonmetals in the compound. For this reason, we cannot call ionic compounds molecules, but rather, we talk about them as formula units. Since ionic bonds are much stronger than our intermolecular forces, we see that ionic solids have much higher melting points. Think, for example, of table salt, or sodium chloride, which has a melting point of 801 degrees Celsius. Zinc blende melts at 1185 degrees Celsius, while cesium chloride melts at 645 degrees Celsius. These melting points are all much higher than what we saw for the molecular solids. Our last category of crystalline solids are made up of atoms. This category is subdivided by the type of atomic unit that makes up the solid, since the three types exhibit very different inter- and intramolecular forces. The non-bonding atomic solids are made up entirely of nonmetal atoms held together by dispersion forces in the solid. Since dispersion forces are the weakest type of intermolecular force, the non-bonding atomic solids will have very low melting points. For example, the non-bonding atomic solids are easy to spot because they are always frozen noble gases. Our next category of atomic solids are made up entirely of metal atoms. Metals are unique in that they possess non-directional metallic bonds, which means that you can think of the metal nuclei as being surrounded by a sea of electrons shared between them. This leads to the unique properties found in metals, including their ability to conduct heat and electricity, to be drawn into thin wires, or ductile, and to be hammered into thin sheets, malleable. The only property you can't rely on to help you characterize metallic solids are the melting points, which tend to vary quite a bit. This is especially true when you consider that mercury is a liquid at room temperature, while gallium is a solid that can melt just from the heat of your hand. What about some other metals? Copper and iridium are both metallic solids that crystallize in a cubic closest packed fashion, while zinc crystallizes in a hexagonal closest packed structure. Both of these closest packed crystal forms are found extensively in the metallic solids, and we'll discuss them further in the next lecture. Finally, we've arrived at our last, and probably hardest to identify, type of crystalline solid. The confusion is present because, while the composite units look like individual molecules, each of these composite units are repeated infinitely throughout the solid and connected to one another through covalent bonds. Let me show you what I mean. There are a very limited number of examples of network covalent solids. My goal is to show you every single one of them so that you can memorize them, which won't be too hard, since the majority are allotropes of carbon. For example, diamond is made of repeating C4 tetrahedra. This means that, essentially, one diamond is one huge carbon molecule. Graphite is similar in that each sheet in the solid is made of interconnected C6 rings. If you strip the layers out of graphite, one at a time, eventually you get a graphene sheet. Graphene sheets are used to make buckyballs, nanotubes, stacked graphene sheets, and a variety of modern materials. These structures can be modified heavily to make some incredibly unique and interesting materials. The last two examples of network covalent solids are silicon dioxide and silicon carbide. Silicon dioxide is made of SiO4 tetrahedra, but because every oxygen is shared between two silicon atoms, we arrive at the SiO2 formula to describe the bulk solid. SiO2, also known as silica or quartz, makes up many silicate minerals found in the Earth's crust. Our last example of a network covalent solid is silicon carbide. So yes, carbon makes an appearance once again. If you've ever used sandpaper, the silicon carbide, or carborundum, could be the source of the grit on the paper you're using. Silicon and carbon can both make 4 bonds each, so the empirical formula for this network covalent solid is SiC. To summarize, when classifying crystalline solids, the first question you need to ask is this solid made of molecules, ions, or atoms? I'd like to offer up this decision tree to help you characterize the crystalline solids. If the solid looks like it is made of a molecule, it could be a molecular solid or a network covalent solid. How do you tell the difference? It's all in the melting point. Recall that true molecular solids are held together with dispersion forces, which results in very low melting points, such as frozen methane, CH4. True network covalent solids will have their composite units, which look like a single molecule, held together with covalent bonds, making them one giant molecule. Covalent bonds are the most difficult type of intramolecular force to break by adding heat energy, so network covalent solids will have the highest melting points. Ionic solids are made of ionic compounds, a metal and a nonmetal, while atomic solids made of frozen noble gases make up our non-bonding atomic solids. Finally, atomic solids made entirely of metal atoms are classified as metallic atomic solids.